Good afternoon, friends. This is a class of mechanics for BSc first semester. Forces of constraint. Well, constraints are related to forces which they restrict the motion of a body, and the forces are known as constraint forces. For example, say a body or a particle moving on the circumference of a circle. So, a particle or a body moving on the circumference of a circle. So, the particle is in contact with the surface. The surface on which body is moving exerts a force on the body, known as force of constraint. Force of constraint. Another example, if we have a rigid body, we know in case of rigid body, distance between any two particles is always constant, and if r is the position vector and say of ith particle, rj is the position vector of jth particle, say rij is the distance between ith particle and jth particle, which is constant. We write this as constant in case of rigid body. Fine. So this distance between any two particles is constant in case of rigid body, and it is always constant, and the constraint here we call it as holonomic constraint. But the action and reaction forces between the two particles or many particles of the body called as constraint forces. So, ith particle exert a force on the jth, and jth particle exert force on the ith. That happens, or that is called as action and reaction force. And this action and reaction force or forces, they are known as forces of constraint. Another example, that is example number 3. Say body is allowed to move on the surface of a sphere. When the body is allowed to move on the surface of a sphere, body is in contact with surface of a sphere. There exists force on the body by the surface of a sphere, and that force we call it as force of constraint, because constraints are related to forces, and these forces restrict the motion of a body, and the forces are known as constraint forces. You can take many examples here, that is 1, 2, 3. One more example you can say is known example to you as well as me here, that is simple pendulum. This is a simple pendulum, this is bob of simple pendulum, right, and this is the length of simple pendulum. We call this as, say, capital L is equal to small l plus r, where r is the radius of the ball in case of simple pendulum. And this ball with this string is fixed at one end. This is a point of fixed point where it is support. And simple example here, that is an example of simple pendulum. Now we have discussed this before also. Here this is a ball of mass m, or a point mass, and it is acting towards the ground, you can say. So its weight is acting in a downward direction. As a result, there exists a tension between, that is, there exists a tension called as force along this thread. Then tension produced in the string due to its weight which is acting in a downward direction, weight is force. And this is acting in downward direction, that is m into z, the acceleration due to gravity. We call it as weight of this. Exactly, in upward direction there exists a force. We call it as a tension produced in the string. And here tension produced in the string we call it as force of constraint. Tension, say, produced in the string is nothing but force of constraint. Force of constraint. This is a force of constraint. Again, in case of rigid body, there is a force of constraint. I will take one more example here. Say this is circular wire, a portion wire, and I want to put a bead. Bead is something like this, and which is having hole in it. It's a bead. It's a solid material. It's a bead, and we can put that bead here like this. Now the bead is sliding along the wire. Bead is sliding along the wire. So during its sliding, wire comes in contact with the bead. B-E-A-D. Bead. Any material which is having hole in and round in shape or oval in shape, we call it as bead, a small tiny object. And when we put it in wire, so this bead is in contact, or bead comes in contact with the wire or a thread in which it is passing through, it is sliding through. So when it comes in contact, this wire exerts force on bead. There is a force of contact called as wire exerts the force on the bead, and that force is known as force of constraint, or the many we call it as forces of constraint. This is an important article as far as classical mechanics is concerned. So the bead is in contact with the wire, and the wire exerts a force on the bead. Force on the bead, and that force we call it as force of constraint. If you look into this article, see the forces of constraint, knowingly or unknowingly, they comes into a mechanical problem which we are interested to solve. There are many examples here. I have given a particle moving on the circumference of a circle. That's another example of rigid body. Say body is moving on the surface of a spherical surface or a simple pendulum or thus. So somewhere when you take an example, they are bound to a force that is known as force of constraint, or constraints are related one or other way, say, to forces, and those forces which restricts the motion of a body known as forces of constraint, and there are many examples here. Well, these forces known as forces of constraint, say, how does they act? What is its nature? Where they act, can we consider or can we take them into account? Well, the forces of constraints are elastic in nature. Their nature is elastic. Elastic in nature. Elastic in nature. What do you mean by forces are elastic in nature? That means they are conservative forces. They are conservative forces. Work done by them sometimes at zero. They do not do any work. So the elastic in nature, they are called as basically conservative in nature. Well, these forces, they exert on the surface of a contact. Forces called as constraint forces, they exert on the surface of contact. When one body is moving or comes in contact with the other, known as forces of constraint. The point here is, these forces are elastic in nature and they are perpendicular to the surface. Say this is a surface and this is a particle or a body which is sliding or moving on this surface. The forces are elastic in nature. They are on the surface, and this force of contact here between this body and the surface of a sphere or any other surface, the force is perpendicular to this is point of contact and force is perpendicular, and the body is moving parallel to the surface. So this is the surface direction which is here parallel to the surface. Such forces, say the forces which are perpendicular to the point of contact or on the surface, and if the body gets displaced parallel to the surface here, then these two, that is displacement and the force, they are perpendicular to each other. They are perpendicular to each other. For example, here this is a horizontal surface. Fine. And say this surface which I have drawn here is frictionless, smooth surface. Almost the friction is zero. A body is moving on it. Body is moving on it. That means, so this is some block of certain mass. When this body is in contact with this frictionless surface, there exists a force of contact known as force of constraint. And this force of constraint is perpendicular to this surface. Body is moving parallel to the surface. This is a perfect example here. That means body may displaced along this direction and the force is perpendicular to the surface. They are at right angles to this other. So work is, by definition, work is force into displacement. Force dot displacement. dot product of two vectors. Here displacement F into D, say F dot ds is work done. Here in this case, because they are perpendicular, if you take the component of this F ds, say cos theta, and theta is 90 degree, and therefore work done cos theta, cos of 90 is 0, and therefore work done is 0. So here in this case, this constraint force doesn't do any work. If constraint force is workless, if constraint force is workless, or say constraint force is not doing any work, or we can say workless, then constraint, sometimes in the literature they call it as ideal constraint. This is ideal constraint, but all the time this constraint forces, they will not do zero work. That means sometimes they do work. It is not ideal all the time. For example, I have here a surface, a horizontal surface, and say this surface is not smooth, and this surface is, say, having some friction. Now, if we are keeping this body on edge and say we are pulling it on this direction, that means we are applying an external force. This is FEXD, external force. We are applying. This surface is having some friction. So because of the friction, there exists a force, what I said, force of contact, and that force is acting in this direction. So this force, because of the external force, there exists another force called as frictional force, and the work is done here. Work will not be zero in case of a surface which is having friction. So sometimes these forces of constraint, they do work. In this example, work will not be zero. If it is work done by the force, that is the force of constraint, is not zero. It is other than zero something. So work may be zero, work may be positive, work may be negative. You know that. So if it is positive, we call this forces as constraint forces, and they are dissipative forces. So sometimes we call it as constraint and ideal, sometimes we call them as not ideal. So for constraint forces, when they do work, right, as in other case here, they are not ideal. Well, if you take Newtonian approach itself, so when we are solving any mechanical or a dynamical problem based on Newton approach, in fact, Newton has not given any prescription for the forces of constraint. He has not given any prescription for the forces of constraint. The other peoples who developed an alternative method, alternative to Newtonian mechanics, called as analytical mechanics, they have given prescription for the forces of constraint. Well, what we have studied here is how does the forces of constraint comes into picture, comes into a problem, and what is their nature? What is their nature? They are elastic in nature, they are conservative sometimes, and then they are always perpendicular to the surface of contact. Surface of contact. See, this constraint, when we use the concept of constraint, we have studied its classification, we have had many examples, holonomic, non-holonomic, say rheonomic, and say celeronomic. We have different kinds of constraint here. Does this constraint raises some difficulties when we are developing or when we are learning an analytical method, an alternate approach to Newtonian mechanics? Well, this constraint introduces two kinds of difficulties. The difficulties introduced by the forces of constraint or constraint. Constraint raises, say, two kind of difficulties. What are those difficulties and how these difficulties are overcome? So, let us say here, consider a system of n particles. A system can consist of n number of particles, and say this n runs from 1, 2, 3, so on up to n. Right? And this system of n particle, so on the system there exists a forces called as externally applied forces, as well as there are some internal forces. The externally applied forces, we can know them, we can take into consideration, we can find out that. Internal forces, like forces of constraint, say they raises or they introduce a kind of difficulty here. Say for example, say F the force exerted on the iron particle of a system containing a number of particles is equal to F say E. This E stands for external applied force plus summation, say I or J runs from 1 to n, because there are n particles, I have taken index n. So, yeah, I you can say here that can be written, yeah, Riz. So, you can write Riz. Fine, Riz. Now, this is the equation we have written using Newton's second law of motion. Say Newton's approach itself. Now, I and J, the internal forces, so action and reaction, or interacting forces. In other words, we call them as interacting forces. Iron particle exert force on J particle, and J particle exert force on I. This term we write It has, say, external applied force. External applied force. Using Newton's second law of motion, we write this as, say, m is the mass of iron particle, d square Ri by dt square. F is equal to m into a, mass into acceleration. We write this. So mi is the mass of iron particle, Ri is its position vector, d square Ri by dt square. Right? So dri by dt is, say, Ri is the displacement, derivative of is velocity, the second derivative of displacement becomes acceleration. So this is equal to Fi E plus summation 0 from 1 to n Fi J. This term, the second term, comes in picture because of the forces of constraint. Now to eliminate this, I have to write this as, say, I runs from 1 to n. This equation we have to write. That is the equation of constraint, and already we have discussed this. Say R1, R2, R3, R4, so on to Rn, and say T, which is equal to 0. This is general equation for a constraint, assuming the constraints are holonomic. Now, looking at this equation, this Ri, the coordinates, they are no longer dependent, means independent. They are no longer independent, they are dependent. They are dependent. That means we don't want here in analytical treatment known as the constraint based treatment of mechanics, we want these coordinates to be independent, minimum number, they must be independent. To make them independent, they are here in this case, they are dependent, and to see their dependency, we write the equation of constraint. We have to write them, and then we have to eliminate those coordinates which are dependent. So this difficulty, that is one, the coordinate dependency. Each coordinate, one coordinate is dependent on the other, and that dependency we have to remove it or we have to eliminate it. This is another difficulty. The second difficulty raised by this constraint and constraint forces, you can say. See, when we formulate in mechanical problem, maybe a dynamical problem, a problem which want to solve, before that one has to formulate. So when we formulate, either we have to know all the forces, that is at the beginning itself, one must know all the forces applied externally as well as forces arises or raised due to internal, say, interaction like action and reaction, contact forces called as forces of constraint. They must be eliminated initially, or we have to formulate a problem so that they disappear on their own. These two difficulties raised by this constraint concept has been solved very easily. One, by using a generalized coordinate concept. What is called as generalized coordinate concept, and shortly we will introduce this. Shortly we will get acquainted with this name called as generalized coordinates. So first difficulty, the dependence of coordinates in a system is removed or eliminated using generalized concept, and for that we must know the basic principle, an alternate form or another form of Newton's law of motion called as D'Albert's principle. To know the generalized coordinates, we must know D'Albert's principle, and this D'Albert's principle is widely used. If you take any engineering textbook on mechanics, they use this principle very effectively, D'Albert's principle. D'Albert's principle is another form of Newton's second law of motion. We will study this in detail. And another concept in classical mechanics here, that is virtual principle of virtual work. Virtual work or principle of virtual work. So we'll leave this based on virtual displacement. Virtual displacement. Generalized coordinates, that is D'Albert's principle and principle of virtual work. We are studying this. These articles are there for our syllabus. Fine. Now the second difficulty raised by these forces of constraint or in general constraint, we will eliminate these forces. See, in mechanical system, one has to know all the forces. Forces must be known, external as well as the forces developed inside a mechanical problem or a system. Internal forces, we will eliminate them as forces of constraint using the equations. Fine. External forces are known to us, we will find out that. We will find the effect of that. So this is how the two difficulties raised by or introduced by what is called as constraint is solved or difficulties are removed. I hope I have cleared here what is called as a concept, that is forces of constraint and the difficulties raised by the constraint. We have solved this. Before we go for the virtual work or principle of virtual work and then D'Albert's principle or generalized coordinates. Generalized coordinates